Yeah. So this is the overview that what are Monte Carlo methods. So Monte Carlo methods or sampling methods basically are approximation techniques. Uh, like earlier we saw variational inference where you can approximate things analytically. Here this is where you are estimating or approximating things experimentally. Let us say I ask you what is the area, what is the value of pi? Then simple possibility is that you take a uniform random variable which can take values in this square, and you know that whatever values this random variable is taking, all those values will be uniformly spread across this sphere. So yeah, they are kind of covering the entire area of the circle, square. They are approximately covering the area of the square, right? And uh, now it's very easy to know whether a point lies inside the circle or outside the circle, right? Because x square plus y square, if it is less than equal to 1, then it is inside the circle. Actually, it won't be equal to 1 in true sense, because it's these are continuous numbers, so real numbers. So it will be either inside or outside. So it's very easy to check whether it is inside or outside. And all those points which are inside, they are approximately covering the area of the circle, and which are outside, they are covering the area outside the circle. So you can use this ratio, the number of points inside this circle divided by the total number of points. That ratio will be proportional to the area of the circle or the circular sector divided by the area of the square, which means pi by 4 divided by 1. So this ratio, this expected value of this indicator function, which basically means the probability of point falling inside, will be approximately this. So this was the basic motivation for Monte Carlo approximation, that we are approximating, and this is the general form which we arrived at, that expected value of any function x, where x is a random variable which comes from the PDF px. So this value, you can analytically evaluate it if you know px and if you know fx, and you can solve this integration or summation, then you can calculate it analytically. But the other way is by approximating it with experiments or with simulations. So where you are sampling your x from this px, yeah, you're sampling this x from px. All those random samples you use to compute this average. You find the average value of f over all those samples, and that is, this quantity is approximately equal to expected value of f x when x is sampled from px, right? This was the basic Monte Carlo estimation. Now we looked at some uses, and yeah, come to rejection sampling. This was an important concept, that how do you sample values from an unknown or a non-standard distribution. No, I won't say an unknown, because it's a known form. Only the form is non-standard. So I don't know how to sample from this QX. Even if I know the expression for QX, I don't know how to sample from it. So I will be assuming, or I will be taking a standard distribution PX. I'm sorry, I think I switched the things. So Px is unknown. Px is a non-standard distribution, whereas Qx is a known distribution. So I don't know how to sample from Px, but Qx, let us say it is a normal distribution. So I will just, okay, I have to find a value capital M such that my Px is always less than or equal to capital M times Qx, right? Qx is a known distribution, and M times Qx is an upper bound on Px. So now you can sample from Qx and use the same thing which we discussed before, that if you want to sample within the circle versus the square. So something similar, that you have now Qx, which is easy to sample from. So you will obtain samples from Qx, and you will just check if your values are lying within QX or not. Sorry, within PX or not. If they are lying within PX, you use them to approximate PX, otherwise you reject them. And in this way, roughly this will be the kind of, you are trying to pick all those points which are lying within this area and reject all those points which are lying outside this area. And that's the idea of rejection sampling. And the form is very simple, that you have an acceptance criteria, that if you are, where is it? Did I write it somewhere? Okay, here it is, sorry. Accept x tilde s with a probability of pxx upon 2qxx. So basically this unidimensional single line. So this much part of this line is within the px and this much is outside. So you take a uniform distribution, or what do you say? You sample from a uniform distribution, and if it is lying below this, then you are accepting. If it is lying here, then you are rejecting it. Let's say this is 0 and 1. This is about 0.5. If your value is between 0 to 0.5, you accept it. If it is beyond 0.5, you reject it. So that was the idea of rejection sampling. And then we went, okay, so here, okay, you know, if capital M is large, then yeah, you can take a standard distribution and take a very large capital M, because assuming that it will contain your px, but then you are losing all these samples, which are approximately m minus 1 times, means the ratio will be m minus 1. So approximately that much you are rejecting. So acceptance rate is only 1 out of every capital M. Okay, then we came to Markov chain Monte Carlo, which basically means that you have two states, let's say a binary distribution, two states, and you know, now you say you don't know the probability of state, but you know transition probabilities. Now this Markov chain Monte Carlo is a game, or is an interplay between two things. One is the probability of the state, the other is the probability of the transition. Probability of transition is represented like probability of S1 given S2, or probability of S2 given S1, since this is a first order Markov chain. So you will say it only depends on the previous state. So probability of xt plus 1 given xt characterizes these transitions completely. So now you want to use this, that what is the relationship between this and probability of x, which is the equilibrium distribution. So we found out that the equilibrium distribution is a stationary distribution, if and most of the time it is stationary, and the condition is that if it satisfies, so this is the relationship between the transition probabilities and the state probabilities. If this relationship is satisfied, then this means that these transitions will, if you let them run sufficiently long, they will converge to, or basically, if you allow this random walk or these random transitions, then after some convergence time, they will be simulating this distribution, phi of x. They will be approximately simulating this distribution. So basically, this is, these are temporal evolutions, right? This is a temporal evolution that you are jumping at every time. And these are the spatial kind of distribution, spatial, how different states are, how probable are the different states, right? So if this condition is satisfied, then it is an it is a stationary distribution pi, which results from these transitions, right? So okay, so let me zoom out. So what I'm saying is there is an interplay between transitions and the state probabilities, transition probabilities and the state probabilities. And the state probabilities are stationary if my transition probabilities satisfy this condition. Basically, or my transition probabilities will converge to this thing if such a pi exists. Okay, now, okay, the question is, given a stationary distribution pi, can I construct the transition probabilities which will converge to that pi? Is the question clear? That given a stationary pi x, the state probabilities, can I construct transition probabilities which will converge to that pi x, right? So here we saw given tx, how do we find pi x? And here we are asking, given pi x, how do we find a tx which satisfies this pi x? So it turns out that there is no one solution to this problem. It can be multiple, because tx is has more number of parameters and pi x is like
6 बजे आज कॉल है क्या? 6 बजे वाले कॉल पे। हाँ नहीं, किस चीज का कॉल है 6 बजे? बल्लेबाजी में फ्रॉड हुआ, उस मीटिंग में मतलब इनविटेशन भेजा है आपने?
muted all. Okay, so sorry for the disturbance. So what we are saying is, okay, given a tx, how do we estimate pi x, or given transition probabilities, how do we estimate the state probabilities? This is what we saw here, and this relationship was obtained. Given tx, how do we estimate pi x? Now the question is, given pi x, how do we estimate tx, or how do we? So it turns out that there are multiple tx which are possible. For example, if there are 3 states, then how many unspecified parameters are there to specify your px completely? If there are 3 states, then to specify their joint distribution, I think it will be a difficult question, because okay, we will not do it. It will take time, and I think we have done that exercise before. So, but these transition probabilities are p of x given the other x, the x1 given x. Okay, in general case, it is p of some new state given the old state. So it is much more variable. So it turns out that multiple t are possible to simulate this, to converge to this stationary state distribution. So what we are doing here is, this is one way to simulate such a tx. And the way is that you do a coordinate descent. Basically, you do not sample from the joint distribution, but you sample from marginals only. So these are my marginals, x1, x2, x3. Obviously, x1 given x2, x3, x2 given x1, x3 given x3 given x1, x2. These are my marginals. So you sample sequentially. First, you sample x1 from these values, and first you start from some random state, and then you sample from p x1 given x2, x3 using the given values of x2, x3. And in this way, you update your x1. Then you sample x2 from this using this updated x1 and the old x3. Then you sample x3 from updated x1 and x2. And this is called Gibbs chain. And did we not prove that it converges to the distribution? Okay, we didn't prove it. So let's start with the proof. Okay, that how can you say that if I sample in this sequence, or if I sample with this algorithm, it will converge to the given pi x, right? That is the question. So my claim is that, or I can say, to prove, we want to prove that, just a minute, give me a second, turn off samples to make my system faster. Okay, so what I want to prove that, okay, I want to prove that if I follow this procedure, then whatever P I will obtain, that will essentially be, what do you say? It will follow this P, right? Which is stationary. Since this is stationary, so it will satisfy this stationary equation, pi x dash equal to t times pi x summation over all x, right? So essentially what I want to prove is that my if I follow this procedure, then this condition is satisfied that pi, I'm calling pi as p of x dash comma y dash comma z dash, where this p is actually like pi, right? This is the stationary distribution which is given to us. Then this is equal to, so basically, if I apply this rule, this algorithm, so Q is my transition probabilities. Okay, let me call it as T, otherwise if you don't, well, okay, let me call it as T. If I follow these transitions from X, Y, Z to X dash, Y dash, Z dash, times P of X, Y, Z, right? Some over all X, Y, Z. Right? Basically, this is the thing. This is the original equation for Markov chain, and we are saying that this is the Gibbs sampling algorithm, Gibbs algorithm, which we have just defined above, right? So we want to prove that with this algorithm, this condition is satisfied. Okay. So what does this algorithm say? This algorithm says that my T is eventually equal to my T. This is eventually equal to. So this is simply the probability of x dash given y comma z, right, times probability of. So now note that this is the true marginal, right, which is computed from the given p. This is not any approximation. This is the true marginal computed from this p, right? Now then this next we sample y, so y dash given. Now my x is actually x dash because I use the sequential sampling, x dash comma z times probability of, then I sample z dash from given basically x dash comma y dash, right? Actually, there is slight misnomer that this is simply p x given y comma z, where what is the probability that x equal to x dash, where y equal to y dash and z, sorry, y equal to y and z equal to z. So it's capital y given x comma z, and this is z given x comma y. So this function marginal PDF is derived from this way, from the original pi, right? So it's a true marginal. Okay, times, okay, it's p x y z here anyways, right? So that's what we want to prove, and I think it's not very difficult to prove. Can you see that? Okay, so first of all, okay, let's look at this. So this is summation over all x y z, and this term has got a z here, and what do we say? Okay. So what we can see here is this is x dash y z. This term has got no x. So this term can come out of this x summation, right? So this yz summation will still remain. Small y, small z summation still remains, but p x dash given yz, p y dash given x dash z. See, this term is also independent of x. This term is also independent of x. So they all can come outside my summation. Z dash given x dash y z y dash. So right, these terms are independent of x, so they can come out. So my summation over x is applying only to x, y, z. And you know what is this term? Yes? Who would like to answer? Somebody can answer. What is this term? Nobody?
Marginal.
Marginal, yes. Tell me the value or the expression function.
P of y comma c.
Yes. So it's P of y comma z simply. Now, oh, this was given by right. This was given. I'm sorry, I made a mistake. Now you see this thing very easily clubs with this thing and this thing. They very easily can get together. So what you see, what is this? If you mix these two or merge these two, what does it become? What does this become? P of
X dash comma
x dash comma y comma z, right? And this term is P of y dash given, given. And this term is actually independent of both y and z, so this term can come out. Right? This term as it is comes out. Now, okay, so you see here, y is not there, right? This y is gone. So this becomes simply, so this thing and this thing, they merge to become what? P of x dash comma z, right? Because y can be summed over, so only summation over z remains. So this becomes eventually equal to summation over z, P of x dash comma z, P of y dash given x dash comma z, and P of z dash given y dash comma x dash. Now, what do you find? These two terms again combine together to give you P of y dash given x dash, sorry, not given, but comma z times P of z dash given x dash y dash. Right? This is summation over all z. And you can see z here can be summed over and this vanishes. So what does this term become? It becomes P of y dash comma x dash. And you see they get multiplied, so you get P of x dash y dash. And that's what was our right hand side. Right? This was my left hand side. Hence proved. Right? So basically what we proved is that if we follow this algorithm for sampling my T, where all these are the true marginals or true conditionals, you can say, sorry, not marginals, but conditionals, then your this procedure will lead to the stationary distribution P XYZ or pi XYZ, which is given to us. So we have successfully been able to find one such procedure which will construct Markov chain to converge to a given pi. Any questions here? To do a demo or to ensure that this actually works, so you can do a demo, take a two-dimensional Gaussian, right here, x1, x2. So you will have a normal x1 comma x2 given some mu1, mu2 comma some covariance matrix, right? So what you will find is this distribution, if you want to sample from this distribution, then you can construct a Markov chain. Like how do you construct a Markov chain? You will say P of x1 given x2 will be what? So this will be some distribution which you can obtain from this normal distribution. It turns out that this should also be a normal distribution, right? And then you can compute, basically follow this procedure and obtain samples, and it will turn out that these samples follow this distribution. How do you verify? How will you verify if the samples follow this distribution? How will you
You
verify?
can find the statistics, the mean and variance.
Yeah, that is one possibility. So to verify, one method is that you, to verify that samples XS follow normal x1 comma x2 vector comma sigma. So one procedure could be from samples estimate mu and sigma. So they will be approximately matching, right? Okay, this is a good method. And any other method? Any other method? Any other method? You can also construct a histogram to do a visual inspection, right? Construct a histogram to visualize. And then you can compute some distance metrics, some metrics. So what are the metrics which you can use? What are the metrics that you can use? Let's say likelihood, right? That likelihood is maximum, or you can use KL divergence. See, yeah, those kind of methods can be used. Okay, now, so you will find out that, yeah, this procedure actually leads to the correct distribution, but given that you have to run it for long time. So the drawback is drawbacks of Gibbs sampling. The drawback, one very obvious drawback is it is very slow to converge. It's also called mixing. Basically, imagine that you have a distribution like this. And in multi-dimension, it is something like, let us say, Gaussian mixture model. Right? So first you sample from here, then you sample from here, then you sample from here, then you sample from here. It takes time to cover the entire space. So it is very slow in convergence because eventually you are moving along the coordinates only. And second is, another reason is that it is, so it is mixing is slow, that is true. Another reason is it is sequential sampling, right? So therefore, again, means you have to go very slowly, like coordinate by coordinate. It's all sequential process. You cannot parallelize it. So that is why it is slow. Although this parallelization can be overcome if you're running multiple chains together, right? If you start from random points and run these algorithms parallelly, basically run parallel chains. So in that way, it can be speeded up or made somewhat parallel. But so these are eventually, and one very important drawback is that it has got high correlation. So what does that mean? It's a very important term to understand. Correlation means, let's say you have a sample XS at some time t, and then you have a sample XS at some time t plus 1. So, between these consecutive things, you will find the correlation is very large, which means that, means intuitively, it means that, let us say this is your entire state space. And if you start from here, you will be moving slightly away, not very much far, but very, very close. So means very long jumps or very large jumps are generally not possible. We are talking about multidimensional space, right? Xs can be huge in dimensions. So let us consider, let's say, 1,000-dimensional X. So you imagine that this method becomes very slow and the successive outcomes are highly correlated. So that is one drawback, and it is actually the drawback in most of the Monte Carlo sampling methods, that the adjoining or the neighboring samples or the successive samples are highly correlated. Okay, now this was the Gibbs sampling method. What can be a possible drawback which you can see in this method? Okay, means algorithmically, or sorry, like samples are correlated and all those things we agree that they are drawbacks, but some other drawback in something which really hinders you in implementation. Means while implementing, you may have serious problem with that issue, so much so that you might not be able to implement it properly. Can you look off? Can you find? Can you see some possible reason that why Gibbs sampling may become actually very difficult or maybe even impossible in some cases? So if I don't know the actual, what do you say, actual marginal, no, conditional distribution, right? If the conditional distribution itself is very difficult to obtain or to sample from, right, then it becomes difficult to use this method, isn't it? If my conditional itself is not very simple, although it's a univariate distribution, it has very nice properties. Univariate is very easy to handle, but still it is not always that easy to handle. And also it may be difficult to derive it in the first place. Right? It may be difficult to find the, what do you say, the analytical expression or the expression for PDF itself. So that these are some difficulties which are associated, or even if you are able to find, then it will be difficult to sample from it. Can we do something else? What would you suggest? Okay, let us say if P is some non-standard PDF, and you know that it's very common to see non-standard PDFs. What will you do in that case? So given whatever we have discussed so far, very easily you can answer this question. If my Px1 given x2, x3 is a non-standard PDF, how will you sample from it?
Rejection sampling.
Yes, very good. We will apply rejection sampling. We will take a standard PDF and then we will apply rejection sampling to obtain samples from this non-standard PDF. Very good. So that method is a very popular method and it is known by the name MH algorithm or Metropolis Hastings algorithm. So what is Metropolis Hastings? So basically it is a Markov chain method where we are applying rejection sampling. Okay, so let's try to derive this algorithm. Basically, we will have to keep in mind the theory of Markov sampling and the theory of rejection sampling. So,
Excuse me, sir.
yeah.
Can I ask just one thing about why is high correlation bad? Why is it not wanted?
Oh, very good question. Why is high correlation bad? Okay. So to be able to get samples from this large distribution or widespread distribution, I should be able to get samples from the entire area, right, roughly, right? But if it is highly correlated, it means I am moving very small steps. My steps are very small, and these are almost correlated. So this means it takes a long time for this random chain to cover the entire area, right? High correlation means the movements are very small, right? So imagine that you have one molecule and in a large room. It will take really long for this molecule to cover the entire room, right? It may take days to cover the entire room. So that is the problem with high correlation, that to be able to cover this entire space, it may take very long time.
Sir, but
yeah,
what we are doing is running a Markov chain till a certain time limit, right?
okay. Means we are not stopping at a particular time. We are just letting it run. So we are letting it run up to a very large time. And
Okay, so and
this is just a 2D, but if you imagine that X is a multidimensional, then it becomes even more difficult.
so we just let a Markov chain run, and suppose we reach an end state or wherever we end.
Yeah.
And we are running multiple of these chains, right?
Yes. Yeah.
And through these multiple chains, we find the distribution.
Yes. Yeah.
So why is high correlation bad? We can just start the multiple chains at different locations.
Good point. So imagine you are starting a new chain. So first you have to sample for a long time to assure that the chain has converged. Right? Imagine come back to this problem which we saw in Markov chains. Yeah, this problem, right? In the beginning, my probabilities are not converged, but after running many times, it converges. So if you have a large dimensional X, it may be 1,000, 10,000. So basically you have to run 10,000 times before it converges. So that time is called burn-in time. So yeah, I can write here. Each chain has a burn-in time, or the time which it requires to equilibrate. So if you are starting a new chain multiple times, then this burn-in time you have to kind of waste or invest. Right? This burn-in time is lost until your chain is in a stationary state.
So my confusion was that where these are samples, right? Sample at t and sample at t+1.
Yeah.
So to get the statistics, we obviously have to take a lot of samples. We have to run many chains.
Yes. No. The idea is okay. The idea here is single chain itself will be able to cover the entire thing.
And we take the values at different time steps to find the distribution, or
yeah, we are saying that these evolution in time, or basically the samples over time, will be able to match the distribution of samples in space. Means my if I let it run in time, so whatever area the chain covers or whatever samples the chain sees, those samples actually match that spatial distribution, the P of X given to us. So it's
okay, so we are using the different time steps, not just the final value.
Because we don't have the final values. We cannot sample from Px directly. That is why we are using chains. Right? I cannot sample from Px directly. Like given the Px, this is difficult to sample, or maybe impossible to sample. I have to approximate. Therefore, I use MC or Markov chain Monte Carlo. So where essentially I have T x to x dash, and I use this temporal distribution and I try to match this spatial distribution. And this matches, if that property that these two are matching, this means I have got ergodicity in my system. Ergodicity means my temporal evolution and spatial distribution, or temporal distribution and spatial distribution are same. Right? Which essentially means this property, where is it? This property, this property is satisfied. Okay.
Okay, thank you, sir.
Yeah, good questions. Okay, now we have arrived at Metropolis Hastings algorithm. So we are applying rejection sampling to Markov chain. Let's start with stating our algorithm first. So the algorithm goes like this. So we take, first of all, okay, it's a iterative process for k equal to 1, 2, so on. So first step is you sample x dash from a wrong distribution, right? We call that as Q. This is basically a transition probability from xk to x dash. K is the time. We can call it as T or K. T or K, basically. Okay, right? You know, in rejection sampling, what do? We have to sample from some P, but we are sampling from some Q. Okay, so here in this case, I'm sampling from this wrong, transition distribution, right? Basically, I will say instead of the P x dash, no, what is it called? Instead of the true distribution. Let me say, okay. Okay, let us come back to this. So, okay, so we have got a wrong sample, and now we want to apply rejection sampling. So basically, we have to have some acceptance probability, right? You saw acceptance probability. So now we say accept this proposal x dash, right? My x dash is the new sample. I will accept it with a probability some probability A of xk to x dash, right? And now what we want to do is, if basically your this is a linear thing, so if you throw a uniform dice, basically a uniform random value generator, and if it is below that number, you will accept. If it is above that number, you reject. And if it is rejected, so if this proposal is rejected, then basically if it is rejected, so accept it. Otherwise, stay at xk. So which essentially means that is your x of k plus 1 or t plus 1 is equal to xk. Right? Or if you would have been here, then you would have said take it as x dash. And if it is rejected, then you take it as or stay at xk. Right? So basically, now if you try to see the bigger picture, what you see is you are generating a random sample x dash and you are accepting it with some probability. So what is the probability that finally you move from xk to xk plus 1 or basically to x dash? What is the transition probability ultimately? Transition that you move from some x to x dash. So for this to happen, so first of all, that you have to be able to generate, right? And then you should be able to accept it. Basically, ultimately your transition probability is a product of two probabilities. One is that you should be able to generate or transition from x to x dash. Secondly, you should be able to accept this transition. So this is, so basically imagine that you have two values here. This is some x1, x2, basically, which is x vector. These are all vectors. I'm sorry, I'm not drawing the bold mark here, but these are all vectors. So what is the probability that I go from this, that is some x to some x dash? The probability to go from here to here is that first you, when you sample from q, and you're not sampling directly, you're sampling on the chain. So q x dash given x. And then the acceptance probability also you have to cross that hurdle, right? Now, this is true for whenever your x dash is not the same as x, right? Because you imagine that if this is rejected, then you stay back at x only. So if your x dash is equal to x, then this will change. So basically t of x to x. What is the probability of staying at the same state? The probability of staying at the same state is basically you make a transition and accept it, or you make a transition to somewhere else and reject it, right? It's like q of x to x times accepting x to x, or else you go from q x to some other x dash, but then you reject it. Now a is a binary probability because it's either is accept or reject. So times 1 minus a x to x dash. Right? Basically, probability that it's rejected. And this x dash could be anything, right? So you have to sum over all x dash, which are essentially not equal to x. So if it is equal to x, then you stay there. If it is not equal to x, then you go somewhere else. Yeah. So that is it. So this is what is my Metropolis Hastings algorithm. So now again you have something which is unspecified. What should be your Q? So again you choose your Q in proper way that you are kind of covering your P. Okay, now let's do some analysis. So the thing is, if I so here I have two things to design. One is the Q and one is the A. So I have to design a Q and then I have to design an A. And this is too much. Like designing two things together is not possible. So remember, in rejection sampling, you use a trick to design your A. What was that trick? What was that trick in rejection sampling to design your A? The trick was you took a ratio of px upon some m times qx, right? There the trick was that, so that in rejection sampling, you only had to design a Q and the A was given by that trick. Here also, can we do some trick to design our A? So let's see. Let's try to put some mathematical analysis to the known things. Like one of the known thing is that if we are going from pi to pi dash, then my stationarity condition should be satisfied. So now we are applying some analysis to find A. So we will not be simply using Q upon or P upon Q, because P x to x dash itself is unknown. We don't know what is the true P because there is no true P in that sense. So what we are trying to do now is analysis to find a good value of A. So what do we have? What information do we have? The only information that we have is so my constraint is that I must satisfy the stationarity condition, which is pi of x dash should be equal to, yes, pi of x times t of x to x dash, and you sum over all x. Right? That is the constraint. I know this constraint should be satisfied. Now, can I use this constraint to find some A? So, first of all, what I notice, there is a principle which says that this constraint is definitely satisfied if I choose another constraint, which is called, so this is satisfied if my pi of x times t of x to x dash is equal to pi of x dash times t of x dash to x. So this is an important, very important equation. This is called the detailed balance principle. It's a very simple concept. So what is the proof? Proof is very simple. You want to prove that if I have this kind of constraint, then this constraint is automatically satisfied. It's just these two constraints are equivalent. So, okay, let us try to prove it. So if this is given to you, does it imply this? So, okay, let's start from the RHS of the constraint. What is it? It is summation over all x, pi x, t of x to x dash. Right? Now, pi is the true distribution and t is the Markov chain which we have defined. Now, t of x to x dash times pi x, this is equal to this thing. I can replace this whole thing with this thing. It becomes pi of x dash times t of x dash to x, summation over all x. Now see, this term is independent of x, so it can come out. And this term is what? This is simply, what you get is pi of x dash times summation over all x, sorry, summation over all x summation over all x t of x dash to x. So what is this? A probability of going from the state x dash to some other state x, and you're summing over all x. Essentially, this term is equal to 1. Right? This is approximately equal to sum tx dash given x, sorry, tx given x dash, and sum over all x, right? I mean, this is something like this, right? So, and you are summing over all x, so of course this will be equal to 1. Right? So basically this term is equal to 1, and what you get is pi of x dash. And that was your RHS or LHS. So what you find is, if you satisfy this property, that being in x and then moving to x dash, and being in x dash moving to x, they are both same. If you satisfy this detailed balance principle, then automatically your stationarity constraint is satisfied. So we will use this constraint to determine my value of A. And how do I do that? It's very easy now. The quest is, okay, now how to choose A. You know, in this equation, where does A appear? Question to you. In this equation, what is the relationship of A, or how can you bring in A into this relation? Yes? Anybody? Anybody?
From T of x given x to x prime is q into a.
Yes, very good. So T is basically a combination of A and Q both. Okay. Well, now one thing is obvious. If x is equal to x prime, then there is nothing to prove. They are just trivially true, right? Only when x is not equal to x prime, then we have to prove. So, okay, let's look at that condition only. So, I know I use my T of, what do you say? Let's say x to x prime is equal to basically some proposal distribution times x to x prime times the acceptance probability of x to x prime. Right? Now I can use this and apply it, use it in this equation. So what do I get here? Pi of x times, what was it? Pi of x times T of x to x prime, which becomes Q of x to x prime times A of x to x prime. This is equal to pi of x prime times Q of x prime to x times A of x prime to x. Right? And this equation is true. Now, can I use this relation basically to, it has both Q and A, and I can use it to find one of, basically to eliminate one of them, either A or Q. Let us eliminate A, because then we know in rejection sampling that A is given to us and we are just designing Q. So here also we fix our A and then we are free to design Q. Now, what does it become? Okay, let us try to put all A terms together. A of x to x prime divided by A of x prime to x. This becomes equal to pi of x prime times Q of x prime to x divided by pi of x times Q of x to x prime. Okay, so let us call this ratio as rho. This is some ratio, some number. Let us call this as rho. We define it as rho, this ratio. Now, what we find that A upon this A of x to x prime upon A of x prime to x is a number rho. So let us assume that rho is less than 1. Let my rho less than 1. Now you know that this is the probability, this is the probability, basically binary probability, right? This is the binary probability, this is the binary probability. Now, and their ratio should be equal to rho. And we are free to design any kind of A. So let us take a very trivial kind of example. Let A x to x prime is equal to rho, and A of x prime to x is equal to 1, right? Then this kind of acceptance ratio, this kind of critic, it's actually, okay, I will just introduce that terminology, that this A is called a critic. And this is called a proposal distribution. Or proposal PDF, you can say. Let me remove this. Basically the true Markov chain. Okay. Now, what we get is, okay, we are satisfying this. So then this critic can be used always, right? This critic can be used. This is a very good critic. So basically, just that my x to x prime should be equal to rho, and x prime to x should be equal to 1. Now it can so happen that this ratio is larger than 1. Then what will I do? Same thing, you take x prime to x as rho. Basically, let us say rho is still less than 1, but this ratio comes out to be, let's say 1. Okay, or else you can say if this rho is larger than 1. So what will you do? You cannot take your ax to x prime as equal to rho, because then rho is larger than 1. How can a PDF be larger than, probability be larger than 1? So what you will do is take A as 1, ax to x prime as 1, and ax prime to x as 1 upon rho, right? Then that will satisfy. If your rho is greater than 1, then choose A of x to x prime equal to 1 and A of x prime to x equal to 1 upon rho, right? Then these are valid probability numbers. So now, okay, it turns out that in the algorithm, we only need ax to x prime. So basically, ax to x prime is very simple, that A x to x prime, this is simply equal to either rho or 1. Basically, it is the minimum of 1 comma rho, right? Whichever is the smaller number, you take it. Because if rho is larger than 1, then take A as 1. If it is less than 1, then take it as rho. That is a very simple critic. So essentially, it becomes, this is equal to minimum of, if I write the whole expression of rho by this whole thing, I can copy paste. Okay, so that's it. This is my acceptance probability. Now, if I choose this acceptance probability, then I am free to choose any Q. Now, what remains is that only Q has to be chosen or designed by you. To be chosen or designed. Q is basically your proposal distribution, that how are you transitioning from X to XZ. So basically what you have obtained. So what you have obtained is, I don't know the exact transition probabilities, but I can either I don't know it, or even if I know it, I don't I don't have, what do you say? I don't have a way to sample from it. Then no problem. I can simply take any wrong proposal distribution and just use it to sample my samples and use a critic to accept my sample. And it turns out that these samples follow my true distribution. Basically, they converge to the true pi. Okay. So now see, in this case, you don't even have to specify a capital M. Like you remember in rejection sampling, you had to specify a capital M, which completely allows your known distribution to what do you say, a known distribution Q to completely submerge your P. In this case, you don't even need your M. But of course, you have to design your Q properly that it is as close to P as possible so that your critic is accepting the things more frequently. Otherwise, it will just reject all your samples. What is the use? And ultimately, you are interested only in accepted samples, right? So and okay, now while choosing this Q, it has to be kept in mind. Choose a Q such that your Q of x2 x dash is greater than 0 for basically for all x dash, for all values of x dash. Why? So this allows you this to for reachability basically. Because if it is 0 for some particular x dash, then you may never be able to reach to that x dash, and your ergodicity property may not be satisfied. Ergodicity means basically that you are sampling in time, which means your transition probabilities, they converge to your remember this condition, ergodicity, and it may not be satisfied if your Q is 0 sometime, right? So this ergodicity property may not be satisfied. So you kind of choose your Q such that it is non-zero. Imagine that you have a one-dimensional case where you have multimodal distribution, let's say 2 Gaussians. And if you are here and you are making jumps and your jumps never allow you to go into the other lobe, then you are just stuck. You can never go to the other lobe. So allow your Q such that you always have are able to reach. Now this how this Q should be chosen. If you choose your, let us say, you want to cover this whole region, and if your Q is very narrow, if your Q is very narrow, then it turns out that it will take a long time to spread across the whole area. It takes too long. Support or not just support, but the area of these dense probabilities, entire area or entire region. And if your Q is too wide, if it is too wide, you imagine that Q is like your how big a jump can you take, right? Like something like in gradient descent, you had a learning rate eta. There it was a scalar, but here Q is a complete PDF. So it is like how big a jump in multi-dimensions can you take. If your Q is very wide, then you are just either rejecting everything, either rejecting all your samples, or you are what do you say, not converging to the right distribution easily. So maybe I can say rejecting mostly. You get your samples rejected mostly. So that's the thing. I think you can simulate these. Like this is a very simple case where this x is a scalar and p of x is also a scalar, and this is your q of x. Q of x to x dash. This is just a kind of Gaussian that you can assume your x is the mean and x dash is the new value which you take around it. So basically you are assuming this is equal to a normal x dash given my mean is x and variance is some 0.01, right? If this variance is very small, then you are diffusing very slowly. If variance is very large, you are diffusing so rapidly that you are mostly rejecting your samples. So, but if your variance is of the suitable length, which is proportional to this spread, then your chain will converge to the true distribution relatively easily. Okay, so I think we can stop here. This was these were some essential things which I wanted to discuss with you. So what we saw broadly, we saw rejection sample. We saw, okay, first the sampling from true PDFs, and then if it is not possible, rejection sampling, then Markov chain Monte Carlo, Markov chains, and then Gibbs sampling, which is one way to construct the Markov chains, and then we used rejection sampling into Markov chains, and we came to Metropolis Hastings algorithm. That is the whole thing what we discussed. Now, the reference for this topic, if you want to study more or you want to study more depth or you want to see some examples, then you can refer to the Bishop's book, right? The Bishop, Christopher M. Bishop. And chapter number 11. So this chapter is called, I think, Sampling Methods, and it discusses many of these things. Yeah. It has some other topics also. If you have interest, you can study, but these are more or less what are essential. Okay, so with that, we can stop here. Thank you very much.
Sir,
Yes.
so in finding out the acceptance A, if we can choose any Q, right? If I choose Q to be symmetric, that x dash to x and x to x dash is same.
Yes.
Then all symmetric Qs will be equivalent, no matter how spread out it is or how thin it is.
Okay. Yeah. Right. So basically, your pi of x dash will be very, very small, and pi x will be large because you are going out of this dense region, and that's why this will be rejected.
All right. So that also makes sense. We have to compensate for the pi's, and essentially, if we can reach make that factor equal to 1, that will be the best case, right?
Yes. So basically, you want your rho to be as close to 1 as possible. Then your sampling will be efficient.
Thank you, sir.
Yeah. So yeah, and the major problem in these algorithms is how can we make the method efficient? Of course, theoretically, we know that it will converge, but how long will it take? It may take years or lifetimes to converge. Theoretically, it converges, but practically it may not be feasible, so or may not be very efficient. So to make it efficient, we choose our Q such that this rho is as close to 1 as possible. Okay, thank you very much, and we can stop here. Okay, bye.